Well, later on we got T.
Welcome back. And the last talk today will be given by Sachin Grover from Harish-Chandra Research Institute from Allahabad,
I don't think
India.
that's not a wall.
Thank you to the organizers for having me here, and so I'll talk about how to construct duality defects in Niemeier Lattice CFTs, and I'll illustrate the construction by the CFTs which have an SO2N type of current algebra. So this work is in collaboration with a postdoc, Subramanya Hegde from IMSc Chennai, and my advisor Dilip Jatkar from HR. So to motivate the construction of duality defects, which are topological objects, I would like to begin with the topological nature of Niemeier charges in 1 plus 1D QFT, for example. So if you have a 1 plus 1D QFT and you have a global continuous symmetry, then we would have a conserved current, which is J mu, and there is some internal index A. And there are Niemeier charges QA, which can be defined as the integral over this J0 part of it, which is the time component, over some, let's say, a closed spatial slice. Okay. And this generator of symmetry is used to write the symmetry operator U of theta, which is part of the group, which is the global continuous symmetry of the QFT. But once you have a Euclidean QFT, you have a freedom what to call time and what to call space. So in this, if you define these operators, symmetry operators U of theta, these operators are topological operators. To see this, we just define an U of theta kind of operator with you have a conserved current J mu, and the conservation equation now takes the form of D star of J. And this is the operator, the symmetry operator. So to see that you deform the group C with some delta deformation, which is some area of the two-dimensional surface, then you expand this, and then you see that this can be written as D of star of J over some manifold M, of which delta is the boundary. And then you see that U of theta C plus delta is just U of theta of C. So you can deform the contour along which we are integrating, and that's why you say that U of theta is a topological operator. So that's how the physical motivation of defining topological operators in 2D CFT occurs. So once you have a 2D CFT, then you would have diffeomorphisms, which are the conformal symmetry generators, and these are the Virasoro generators, these LNs, which are about translations on a cylinder, etc., that we'll talk about. And these X's are the topological operators. So they commute with the Virasoro generators in both holomorphic and the anti-holomorphic part. But these line operators do not necessarily commute with an extended algebra, which is a bigger algebra, of which the Virasoro algebra is a part of. And to understand now in a Euclidean setup, we would need to choose a direction of time. So for that, we use the most common radial quantization picture of a 2D CFT. And in this picture, we take the plane of the complex plane and map it to a cylinder. And then from cylinder, you can see that how do we define an equal time slices. So this S1 circle is just an equal time slice. So this direction, the non-compact direction, is the time direction, and the compact direction is the spatial direction. So the line operators would have two kinds of meaning. One is the operator meaning. So you had an operator and you define the action of the operator on a local state, and you can also define that as a defect. So what do we mean by this is that if you have an operator encircling the spatial slice, the S1, then you would have this action, which we'll define shortly, on a local operator, which is a state in the Hilbert space of the CFT. What you can also do is you just map the two ends of the cylinder and make it a torus, and then on the torus we define modular transformations, which are the SL2Z transformation, and one of the generators is the S transformation, which takes this cycle to the longer cycle, like the A cycle to the B cycle on the torus. Right? So this is an operator which acts on a state which comes at minus infinity, in the time direction, but this is a defect which is attached to an operator on the spatial slice at -infinity. So what do we have here? So if you think of this as you're looking at from the top of the cylinder, and this object is the state which is at -infinity, and there it meets an operator at some finite time slice, and then you get the state which is x times phi of z. So this could be like some charge operator which charges the state, and this is just some number in some sense. Okay. So notice that once you have these kind of operators, then you would have a Hilbert space of states which phi z is a part of. Then you map the Hilbert space to the Hilbert space h of x. This h of x Hilbert space could in some sense be a smaller Hilbert space because you would have maybe a charge which is 0 for some state, and then you would say that you have a projection kind of an operator. And once you have this operator which is a projection operator, then you would think that you could have a non-invertibility of this operator, because if you go from a bigger Hilbert space to a smaller Hilbert space, there is no going back, right? So now the X operator is a topological operator. This would mean that it commutes with all Virasoro generators, which means that the conformal dimension of the operator, which is the L0 eigenvalue of phi of z, is preserved. Okay, so the energy is the same for both the states. So to define the non-invertibility of an operator much more seriously, then we need to define a fusion of two operators. By that we mean that if you have two circles which are the operators xi's and xj, which meet the state one after the other, then you can define the fusion of these two line operators as a simple decomposition over simple line operators. So xk's are line operators on the right hand side, and this is a statement that need to be understood inside the correlators of the CFT. Okay. And this is a generalization of the usual group multiplication that we have in group-like symmetries, which are the usual symmetries that we study. So pictorially we can describe these as two lines, and there are some local insertions on the cylinder. Then you can see that if you think of them like group-like objects, then there is a group multiplication law between UG1 and UG2, which gives you UG1, G2, and this follows some group multiplication law, and the operators are left intact, the local insertions. But in general, you can define for two line operators to fuse like this, where the right hand side does not contain just one single line, but a sum over simple lines. Okay. And this is the fusion algebra corresponding to that. So an example is an easing CFT, which is a critical easing model at criticality, which has a central charge half, but then there are three primary operators, meaning that there are three modules associated to the identity, epsilon, and the sigma primary states. So these are the highest weight primaries, and they have the L0 and L0 bar eigenvalues, which are 0, 0 and half, and 116, 116 for these three states. Okay. What we can think of now, adding line operators in the cylinder setup. Now this line operators would be L, denoted by L, and they can act on the primary states in this fashion. Since you know that the L's are topological operators, we know that these operators would give only numbers on the right hand side, because you would have L0 or L-1 action on these states, and then you would know that these the small L0s and L-halves, these are numbers. Okay. So they belong to, for now, some real number. So just a background on what are the conditions that we require when we say that we want to define a defect is that you would define a partition function of a 2D CFT in terms of these characters, which are the Q series, and the Q is just e to the power 2 pi I tau, where tau is the modular parameter of the torus, and these AIs are the coefficients which tells you the dimension of the nth eigengrade. So this n value is that, and I would correspond to some ith primary in the inner CFT. So because you're on a torus, you could define modular S and T transformations, which would take the torus parameter from tau to -1 over tau, and then the characters transform as follows. So these Sij's are some numbers which tells you the modular S matrix of the CFT. So this is a theory dependent number that we get. So the partition function can be written in terms of these characters, which are the building blocks. So these Mij's are the corresponding coefficients for the characters, and these are all going to be positive because they tell you how many characters are there in your CFT. So how many modules of a particular kind are there in your CFT. So the easing model example that we were looking at would have this character, or this partition function written in terms of these characters. So this would be the vacuum, the epsilon1 and the sigma. All three contribute equally, and then you can write the partition function like this. Now once you insert a line operator, you charge all your states, and then you would get the eigenvalue L0, L half and L1 over 16 accompanying these characters, because inside the trace it acts on one of the state, and then the number comes out. Okay, so there is no square etc. of these numbers. So since L is topological, it commutes with the test tensor modes. This means that the entire number, this L0, comes out from the entire module. So note that for the insertion partition function, we do not require these numbers to be positive, but once we require it to be some partition function of a CFT, these numbers are positive because these numbers would tell you how many states are there in your particular Hilbert space. So what to do with this is, like, you have this picture of an operator, okay, the orange line, and then we map it by a modular transformation to a defect. So this would mean that you now have a defect Hilbert space which is quantized on the S1 slice, and then you would have the partition function written as follows. Okay. So this partition function would be written in terms of some coefficients Mij times the character of the CFT, and this can be computed by knowing the modular S matrices of the characters. So once you impose only the positivity of the coefficients, and that is what tells you the dimension of the Hilbert space, only that constraint is enough to tell you that there are only three possible sets of L0, L half and L1 over 16 eigenvalues, which means that there are three possible line operators only. These we write as the identity line because the charges on all states are 1, so it leaves every state exactly invariant. But then there is one operator which is eta, which charges only one state, the sigma state, to -1 and all its descendants. And then there is one state which is like a projection operator. So it takes the sigma state to the 0 state in some sense. Okay. So this would mean that this is a non-invertible operator. So to understand this, so what we do is, like, you subsequently act the operators one by one on the state, and then you find that eta square would give you just the identity line. The n line with eta line would give you the n line back again. But then if you apply n squared, you will get that you get 1 plus eta, right? And then because there are only these three operators, there is no extra operator which would say that there is an inverse of n under the fusion algebra, right? So this fusion algebra you can start with, and you can find out all the associators of the fusion category, and then what Tambarai and Yamagami did was to find that what are the possible fusion categories, and this would tell you exactly up to some epsilon constant that we'll talk about later. So to understand this, if you have this green region marked as a theory, and then you have a line inserted inside, which is the n line, then you insert the n line back again, so this is in the green region, then you get the identity lines, which means that no action inside the theory is the theory exactly, and then you have an eta line, which is the invertible line, which is a symmetry. So if that eta line would give you the theory back. So in our setups, we look at Niemeier Lattice CFTs, which are CFTs corresponding to a simply less current algebra at level 1 and the central charge 24. And these CFTs are meromorphic CFTs, which mean that the correlators are all meromorphic functions of the coordinates z. and these can be decomposed into a holomorphic piece and an anti-holomorphic piece. So one functions of z and z bars. Okay. And this can be only done when the central charge is an integer multiple of 8. So 24 is special because at c equals to 24, you'll get an exactly modular covariant, modular invariant chiral factor. So the current algebra looks like this. So you have JAJB, which would be this part is the usual Lie algebra part, and then you have the affine part with some level k, which will take it to be 1. So once you take the level 1, you will define the central charge from the Sugawara construction to be just the rank of your Lie algebra, which we want it to be 24 since we're looking at C equals 24 CFTs. And our construction only is valid for simply laced algebras. This is ADE type algebras because we only require free bosons to construct such a CFT. So the lattice looks like this. So you have roots of your Lie algebra, and then you take the Z lattice over this, which is the root lattice, and then you can also do the same thing with the fundamental weights to construct the weight lattice. Okay. So the Dn type lattice you can choose some coordinate, and then this coordinate you will get that the root lattice you can write in terms of these integers k1 to kn, where sum over ki would be 0 mod 2, so these are even numbers, the sum. And then you can define the three other representations of Dn type, which are spinor, the conjugate spinor, and the vector representation of the SO2n algebra, right? And these are the primaries of your CFT. So these are the all possible primaries you can have in your CFT. So the fusion algebra in lattice point of view is just lattice addition. So if you take any two vectors of any conjugacy classes, X, you will get the root conjugacy class, and similarly you can do the procedure with S and V conjugacy classes to get the C. So it's like you take any two and you get the third. So if you add any one conjugacy class back to itself, you get the root conjugacy class, and that's the fusion algebra of the local operators in your CFT. So to construct the CFT from this lattice, you associate a state to every lattice point, and by that we mean that you construct a vertex operator gamma alpha, where alpha is the root lattice, and this acts on the vacuum to write a state in the Hilbert space of the CFT. But then you can also write chiral oscillators, which is the part written here, which has this algebra, and a general state then can be written as some excitation of the state, which you write by acting the vertex operator on the vacuum. Okay. And then you can define a conformal dimension by defining a grade in your Hilbert space. So this is a graded Hilbert space, and then the conformal dimension can be defined by the grade n, and then the norm of the lattice vector, half times the norm of the lattice vector. So you can combine everything simply into one boson field, which we define as a simple boson field in string theory, for example, from the world sheet. So what you do is you define these oscillators A's, and you have the momentum state which labels your root vector, but then you also need to define a position operator. But then a position and a momentum operator cannot simultaneously be written, so you need to exponentiate it, and then you write the vertex operator like this, which is e to the power I alpha dot phi of z. Okay. And the algebra is the same algebra as you would require for your affine Kac-Moody algebra. So you have the vertex operator in a representation of your affine Kac-Moody algebra like this. Okay. So the Cartans we choose to be just the partial derivatives of the chiral part of it, the phi of A of z, which is not completely chiral because you have a zero mode here. And so you write the representation of your algebra like this. So now you can look at the CFT states. Okay. So the lattice and the bosonic CFT are mapped like this. So if you have lattice n with a dimension n, then you have a central charge n. And then every lattice point you can define a state, and the half length of the lattice vector is the conformal dimension. Then if you define the lattice to be even, which means that you would have all even lengths, then you would say that the conformal dimension is always integer, which is what is the mirror morphicity condition all about. Then if the lattice is self-dual, then it can be mapped to the statement that the conformal field theory is modular invariant. That is, the partition function etc. that you write is a modular invariant object. So the Niemeier lattices that we want to look at with D-type algebra are the following. So it is D24, D12 squared, D8 cube, D6 to the power 4 and D4 to the power 6. And these are the generators which are required to write all possible primaries such that your lattice is an even self-dual lattice. So the duality defect are this. So if you have a symmetry of your theory, which we'll call eta, as similar to what we did in Ising model, then you can define an orbifold of your theory with the orbifold partition function given as, so this partition function is without any insertion, the partition function with the eta above is the spatial insertion, and then the eta down is the time-lag insertion, and then eta would mean that both space and time-lag insertion. So this combination is a modular invariant combination, so the A and B cycles are correctly aligned. And then the CFT is non-anomalous once you have the T square action, the modular T action on the partition function given like this, where the modular S transformation would take you from the A cycle to B cycle, so that eta upper is defined with Z lower eta once you act S modular transformation on it. Okay. So the category of group-like symmetries is what we say when we want to extend the group of symmetries with a non-invertible duality defect, and this extension takes you from a group to a category. So Z of curly n is defined as the trace over the Hilbert space with the n insertion, which can be defined as this operator. So you take 1 plus eta by 2, which maps you to a part of the Hilbert space which is left invariant under eta, and then you define this G outer automorphism which takes the invariant sector to itself, but the non-invariant part is mapped to some other part of the CFT, which would be the dual CFT in the orbifold sense. Okay. So now you define the Zn squared action, and then you see, because 1 plus eta is like a projection operator, so 1 plus eta squared would give you just 1 plus eta, and G is a Z2 outer automorphism, so G squared gives you 1, and the root 2 squared cancels with this half factor, then you'll get the fusion algebra what we wanted as we see in the Ising model case. So that is the Z2 Tambara-Yamagami fusion category. Okay. So the eta symmetries can be characterized by the action that they do not change the vacuum state and they do not change the stress energy tensor. So this means that the grading etc. is preserved in your CFT, the central charge is preserved in your CFT once you have the symmetry. Okay. So the next excited states are above the vacuum are of the form JA minus 1 acting on the vacuum, where A is the adjoint index of your symmetry, the affine Kac-Moody symmetry. So now this A index takes values in the finite part of the Lie group. Then you have this index to play around, which means that the symmetries are the automorphisms of the finite Lie algebra. And the automorphisms are of the finite Lie algebra together with the exchange symmetries that you have, for example, D12 squared factors, then you can take the exchange between these two CFTs, between these two factors of the CFT, then you can get another automorphism that is an outer automorphism of your algebra. So the discrete symmetries are used to construct the orbifold symmetry, and once we find that the orbifold symmetry, orbifold CFT is the same as the original CFT, it's a dual description of your CFT, then you proceed to construct the duality defect. So for example, look at the most simple one. So if you have D24 CFT, then you have two primaries there. One is the vacuum and one is the spinor module. And the partition function can be written in terms of the Jacobi theta functions as follows in this equation. And then what you can do is you think that you can just replace the spinor module by the conjugate spinor module, because you're not calculating the charges of the of the D24 algebra. It's just the energy that you're calculating. So you can just replace the spinor with the conjugate spinor with the same partition function, right? So you would say that these two CFTs are dual of each other. And the way to construct it from a lattice point of view is you start with the 0, the vacuum, and together with the S, but then with the non-invariant part, the S part, you add the vector conjugacy class to get the C, right? This is what you would think, like if you think in terms of a lattice. And that is the construction that we will do to write the lattice partition function of a CFT, starting from an orbifold CFT first. So the inner automorphisms of the Lie algebra are known from Karz's theorem. So what you do is you define an X vector in terms of the fundamental weights of your finite Lie algebra with some positive numbers SIs, which can be obtained from the marks of the Lie algebra, and then you can define the action of the inner automorphism on lifted to the vertex operator algebras. So the gamma alpha etc. transforms in this way, where you have a spinor projection part. So because the spinor representation is not a proper representation of the SO2n group, it's a representation of the spin group, and there is a Z2 factor that you can attach here because you're looking at SO2n representations. So this is the factor, the projective factor, and the oscillator modes are left untouched once you look at inner automorphisms. So the anomaly check can also be made. So for example, I showed you that t squared acting on the partition function z eta should keep it invariant, and that is how you check whether your theory has an anomaly or not once you want to orbifold your CFT with a particular symmetry. Then in the lattice picture, it's a very fast procedure to check how to show that you will have anomaly free symmetry or not. So what you do is you start with your lattice, which is L0 and L minus L0. So the lattice is L, so take a union of the first column, you'll get L. But then there are other parts in the lattice. So this X vector from Karz's theorem, you use this vector to construct two other possible conjugacy classes in the lattice. Okay. What we find is that if you have the norm of the vector X in even integer, then you use this prescription to define the orbifold lattice. If you have an odd integer, then you define the second prescription, which is this obvious choices in between L0 and the remaining lattice to define your orbifold lattice. Okay. But if x dot x is not an integer, then the symmetry is found to be anomalous. Okay. So this is true. So for example, you can see that you'll get in D24, you have like lots of possible options of eliminating nodes in D24. But then you have only 3 possible orbifolds. With current algebras, you'll get either D24, D16 times E8 or D12 squared. So what is left now is to look at the outer automorphisms of the finite Lie algebra. So what you do is you look at the Dynkin diagrams and then you mark out what are the possible outer automorphism symmetries, which are the symmetries of the Dynkin diagrams. So for example, any D type would have this kind of symmetry, and D4s would have the remaining 4 kind of symmetry along with this 5th symmetry. So these are the ones which are listed here. Okay. And what we find is that now these outer automorphisms serve as your G symmetry in the partition function that we saw earlier. And what you do is you replace in the invariant sector, one part of it with these replacement rules, and you get the partition function with the capital N insertion, which is the duality defect insertion inside your partition function. So it comes as simple as that from a lattice prescription. So one example that I can show you is about the D24 CFT. So you start with the 0 and the S primary, the vacuum and the spinor primaries, and then you write the D24 in terms of D4 and D20 conjugacy classes. And then you say that you want to write a Z2 symmetry, and the symmetry is this. So the symmetry we get from Karz's theorem would charge these vertex operators and leave all the other vertex operators invariant. Okay. And this is the orbifold partition function that you can define. So you see that 0, 0 and SS part is the one which is invariant, where the VV and CC part is changed to this in the orbifold theta. So it's not the same CFT, so it's not the symmetry, it's a duality between these symmetries that the N operator, the curly N operator would do next. So to construct that, you find that there is one outer automorphism symmetry which changes these factors and keeps the invariant part as it is. And this you can do it in two ways. So you look at the twisted Dynkin diagrams and then you calculate what are the x vectors and then calculate what are the charges on the vertex operators, etc. to calculate the partition function finally. So this partition function can be written in terms of the characters of SON algebra. These are the finite characters, and these are the characters for the affine Kashmiri algebra, sorry. And then you notice that you'll get minus signs instead of the usual plus signs for a CFT, because now this is one charged operator insertion which is inside. Once you do a modular S transformation and drop the n from the superscript to the subscript, then you'll see that these would give you a proper Q series with positive integer coefficients, which are the dimensions of your Hilbert space. So summarily, so what we did is to construct topological defects. The main goal is to construct topological defects in 2D CFTs. So what we saw that in 2D CFTs, we have conserved operators in Lorentzian QFTs, which are topological operators in a Euclidean CFT. Okay. So now we looked at some particular DN type Niemeier lattice CFTs which have this algebra D24, D12 squared, D8 cubed, D64 or D4 to the power 6. Only these are allowed. And then we looked at some features of it. So these are meromorphicity, and then you also have a free field representation, which is in terms of 24 free bosons of these CFTs. So remember that all of these CFTs have the same Lagrangian. They have the same Lagrangian of 24 free bosons, but then it's the choice of vertex operators which tells you what are the possible options that you can, what are the possible current algebra that you can write for these CFTs. So what we did is, now in the process of finding out all duality defects, we found out the Z2 orbifolds of these CFTs, and then we proceeded to find duality defects in these CFTs, and then because we know all eta lines and we know all the duality defect lines, we know that these n curly n lines, these are non-invertible in nature because of fusion algebra, and for every time we wrote the non-invertible fusion algebra, we wrote the defect partition functions, where we saw one example of D24 at level 1 CFT. So the immediate question is, what other type of defects are there in your CFT? So it could be just not duality defects, but then there could be other kinds of defects in your CFT. We have not looked at those. Then you could have odd lattices which correspond to non-semi-simply laced lattices, right? And then what are the duality defects pertaining to those? That also we did not look at. The last part is that, okay, so now you have in your worldsheet CFT, you would have defects, but then what do you gain from it in the string theory setting? So the C equals to 24 CFTs, these are relevant for the n equals to 0, 2 heterotic string theories. So these string theories has a n equals to 2 supersymmetry in one of the chiral sectors. You can take, for example, the right chiral sector, and no supersymmetry in the left chiral sector. Then the critical dimension that you can calculate for these strings is 2 dimensions. So what you can do is you start with the bosonic string in 26 dimensions and then compactify along the Niemeier lattices in 24 dimensions. And then you get the n equals to 2 heterotic string theories. So then the question would be that you have defects in your CFT. What do you know about the n equals to 2 heterotic string theories? Do you think there's a duality between these string theories or not? And that is the question that we'll like to answer next. So thank you.
Questions?
Did you explain why you focus on this D series only?
Okay. So in Shelikin's list, there are a lot of CFTs which are of different current algebras. The D ones are very interesting because you would have a lot of outer automorphisms to play around with. So A-type Dinkin diagram is just one single line. So there's only one Z2 symmetry, which is just you take the Dinkin diagram and reflect it. But in D-type, you have lots of outer automorphisms, and then you would find lots of duality defects, in principle, you would think. But then there is only one extension of the symmetry that you can find. So there is one, every time you find a eta, you find only one capital N line. So that is why it's more interesting than A-type, etc. And then
But other types, like, I mean,
so
E,
E-type,
B, C,
etc.
whatever.
also has like very less outer automorphism, and the remaining ones are not simply laced. So the lattice is not simply laced. So then you would have you need interacting fermions in your description of your Lagrangian, and that complicates how you would write the vertex operator algebra for those CFTs.
What is the fusion category of topological operators you got in the end? Was it again a Tambara Yamagami?
Yes, it's an extension. So if you start with the Z2 symmetry eta, then you get one extended line, which is one non-invertible line, which is curly n, which is in the Tambara Yamagami category.
Other questions? Okay, so let's thank Sachin again.